Okay, this lecture is on Module 7 of your curriculum, which is entitled Ethernet Switching. So we'll go look at the introduction, which starts out with, why should I take this module? The short version is we're going to learn about Ethernet and Ethernet switching and some related information in Module 7. In particular, we're going to talk a little bit more about Ethernet frames, which we mentioned, I believe, in Module 6. We'll go back and talk about source and destination MAC addresses, which we've mentioned before. We'll talk about the MAC address table. We'll talk about switching speeds, switching duplex, and several forwarding methods as we talk about that. So if we go to 7.1, which is called Ethernet frames, the first thing they talk about is encapsulation. So basically what we're doing is we're taking an IP packet from layer 3 of the OSI model, and we're going to encapsulate that into a frame, in particular an Ethernet frame. And then if we look down, if we skip ahead down here, this is all happening at the data link layer, and then we're going to convert that frame to ones and zeros and send over the physical media like we have seen before. There are different speeds for Ethernet. A long time ago in the 70s, it was 10 megabits. It was 10 megabits per second until about 1989. And then 100 megabit Ethernet came out. About 4 years later, gig Ethernet, or 1,000 megabit per second Ethernet, came out. And then since then, we've gotten 10 gig, 40 gig, and 100 gig Ethernet. So same technology, that we've been using for 4 or 5 decades, but as time goes by, the speed that we can transmit these bits over the network has greatly increased from when Ethernet was originally created. Looking down here, we talked about standards in previous modules. They don't have it down here, but IEEE, the Institute of Electrical and Electronics Engineer, controls the specification for Ethernet. In particular, IEEE 802 is computer networking. 802.3 is Ethernet. As we'll see a little later, I think 802.11 is wireless. 802.15 is Bluetooth. And 802.2 talks about the logical link control, or the upper portion, or the upper sublayer of the data link layer of the OSI model. So talking about that here, they actually mention IEEE 802 and talk about that. And they talk about the sublayers that we talked about here, the media access control and the logical link control sublayers. So the logical link control sublayer is what's going to communicate with the upper layer, so layer 3, and then it's going to place that on hardware in the lower level, in particular the media access control, which is what's going to prepare the frame and place it on the physical layer. So here they're showing the physical layer, layer 1, the data link layer, layer 2, the network layer, layer 3. So at layer 3, that's typically the network layer protocol that we most commonly talk about in this class is IP. IP version 4 and IP version 6. The physical layer, of course, is the media, the NIC cards, that type of thing. 802.2 reads information from layer 3, prepares it for the hardware, and depending upon whether it's wireless LAN, wireless PAN, for example, Bluetooth, or Ethernet, are different standards for placing that on whatever the physical media is. So in the MAC sublayer, the media access control sublayer, we have encapsulation. Again, I said this a little bit ago. It's taking IP packets and packing them into Ethernet frames. We have the frame itself. we have to deal with addressing. At layer 2, the mechanism we use for communicating with other devices on the same local area network is the MAC addresses. So we'll have source and destination MAC addresses. And then we talked about this previously, but we'll talk about it again, having a frame check sequence to make sure that the frame made it to its destination intact. So this is just the same diagram that we saw before. They're refreshing your knowledge a little bit. In the past, when we had hubs, we had to worry about shared, half duplex, medium. We talked about carrier sense, multiple access collision detection. We talked about carrier sense, multiple access collision avoidance. So we'll come back and talk about those a little bit towards the end of this module. So the Ethernet frame itself, they have it depicted here as 6 boxes. When I do this, I like to do it as 7 boxes. I like to divide that first box in half. Kind of alluded to that a little in the previous module, but talk about it in more detail here in a moment. So Ethernet frames are relatively small. They're anywhere, the smallest is 64 bytes. The largest is 1,518 bytes. So anything we're transmitting is broken into these very small Ethernet frames and sent across the network. Talking about these in detail, like I said, this first part is shown as 8 bytes. While technically correct, I'm going to show it as 7 bytes followed by 1 byte, the start frame delimiter, what they have labeled here is the SFD. And we talked about this last time. So there are 7 bytes of the preamble that are transmitted. And devices on the local area network that are trying to read this frame first have to kind of lock onto the frame and know where the bit time transactions or transitions are happening so that it can read the ones and zeros. So this preamble is just a string of 01, 01, 01, 01, 01, 01, 01, so that the devices can lock on to the frame that's being transmitted. They may not see all 7 bytes, but 7 bytes is enough for them to lock on at some point and be confident that they're reading the frame bits correctly. And then what happens is you get to the start frame delimiter, and the start frame delimiter goes 01, 01, 01, 11. And as soon as the NIC cards see that 11, they know that they now have the Ethernet frame that they need to read. So that actual frame is considered to be from after the start frame delimiter to the end of the frame check sequence. So what happens is the first thing we have is the destination MAC address. So I've asked you several times and you need to be able to quickly say, oh, a MAC address is 48 bits. Well, 48 bits is 6 bytes. 48 divided by 8, the size of a byte is 6. Then we have the source MAC address, which is also 6 bytes, or 48 bits. So the frame is going from the device that has this MAC address to the device that has this MAC address. Last time in Module 6, I think this was just simply labeled type, and I told you that it might be a type or a length. So depending upon the value that's stored here, will determine whether that is a type or a length. Then we have 45 to 1500 bytes. If you've ever looked at any networking configuration, you may have seen something called MTU, which is maximum transfer unit. And it is usually set to 1500 because that's the maximum amount of data that can be transmitted in an Ethernet frame. After the data portion, we then have 4 bytes, which is 32 bits, of a frame check sequence. We'll see an example of verifying this, but basically, as this frame is sent, a mathematical operation is performed. We end up with a 32-bit value. We stick that in the frame check sequence. And then as the frame is received, once it sees the start frame delimiter, it starts performing the exact same arithmetic calculation. It ends up with a 32-bit number. If the 32-bit number it comes up with exactly matches the 32-bit number that's in the frame check sequence, then we assume that that packet arrived intact or is valid. 715 is a check your understanding on Ethernet switching. So after you go back and study the material we just discussed, you can go over that yourself. 716 is a lab, and you are going to use Wireshark to look at Ethernet frames on your local PC. I will be assigning this lab, so watch for it to appear in Blackboard. In section 7.2, we're going to talk a little bit more about MAC addresses. MAC addresses, like I have said a number of times, are 48 bits. They're refreshing your memory from, I think, Module 5 on number systems, that when we have hexadecimal, our digits are 0 through 15, which can be represented as 0 through the letter F. And here's the binary values. You know, this is 0, this is 8, this is 10 or A, this is 15 or F. So you can go back and refresh your memory. Now what they're showing you here is that a byte can very nicely be represented as 2 hexadecimal digits. You know, if we take 128 for example, this is the binary representation in a byte for 128. If we kind of divide this in the middle, 1000 is 8, and then 4 zeros is 0. So we have 80 hexadecimal. The maximum value we can have in a byte is 255, which is all ones. 4 ones is an F, 4 more ones is an F. So we represent a byte that has the value 255 in it as FF in hexadecimal. So they're just refreshing your memory of that. Down here, when you represent a base 16 number, when I did it, I believe in my number systems lecture, I used a subscript of 16 to represent the base. Since a lot of text editors and things don't have subscripts, obviously Word does, but other things may not. Probably the most common, and what I'd even go as far as say is the preferred method, is to put a 0x in front of the number. So if you had 0x FF, then that's saying I'm doing FF in hexadecimal. Another way, which I don't consider preferred or really even that common, is right here, which is to put an H after it. So 73H would say this is 73 in hexadecimal. So that's just how you can communicate that information to someone. 722 is talking about the MAC address. I think we've mentioned this before, but to refresh your memory, every network device has a NIC card, NIC, network interface card. That card is going to have a unique address or sequence of ones and zeros represented or written into it. That is supposed to be unique in the world, and that is referred to as the MAC address of the device. So down here they're showing you if we have 48 bits and we can convert that to 12 hexadecimal digits, and then we can take pairs of hexadecimal digits to basically end up with 6 bytes. The next thing they talk about down here is the organizationally unique identifier. That is the first half, or the first 24 bits of the MAC address. And the organizationally unique basically means this is going to tell you who made the device. Now down here they're showing MAC addresses with dashes between the bytes. I would say typically in real life it's more common to use colons, but using dash after every byte, using colons after every byte, or using periods after every 2 bytes are usually the most common way to represent Ethernet MAC addresses. So down here they're saying if you have a MAC address that starts with 00602F, that was assigned to Cisco. So that basically tells you whatever NIC card you're looking at was made by Cisco. I think 000F00 and 0000F1, or maybe it was 0F01 were Next Computer. So I will give you some of these to look up in a future homework assignment. But that's the organizationally unique identifier. Okay, 723 is talking about the processing of frames. Just want to point out that a MAC address, they mentioned, may be called a burned-in address. I hardly ever have heard it referred to that. It may be referred to a hardware address or a physical address, are probably the 2 other most common things that I've heard the MAC address called. Down here, of course, the source MAC is the MAC address of the NIC sending the frame. The destination MAC address is where the frame is going. So down here in this animation, host 1 up here is wanting to send a frame to host 3 down here. So what will happen is it will send the frame out. It will pass through the switch. The packet may go out other ports of the switch based on what we're going to talk about here in a moment. But if it has flooded out all the ports, all these devices are going to see it, and H3 is going to say, hey, the destination MAC address is me, so I'm going to process the packet. H2 and H4 will look at the destination MAC address. It will not mention their MAC, or will not match their MAC addresses, so they will ignore the packet. .724 is talking about unicast addresses. We will talk about broadcast and multicast as we did before. But the source is always a unicast MAC address. It is the MAC address of a single machine. If we're sending this to a single destination machine, then the destination MAC address will also be a unicast address. So here we have a figure. So right now we're just looking at MAC addresses. The source MAC address is host 1. The destination MAC address is this server. So if we send this, what will happen is, if we assume the switch knows where everything is, the packet will just go out the port that the server is connected to. So these other machines won't even see the packet. And like I said, it's kind of a chicken and egg thing. We haven't talked about a fully populated MAC address table yet. But this is assuming that the switch does have a fully populated MAC address table, which means it knows the MAC address of all these machines and what port they are on. A broadcast is one to all, with the caveat that all means all the machines on the same network. At layer 2, a MAC broadcast address is all ones, which would be FF, 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 FF. So what happens here is we'll see that the source MAC is host 1 again. The destination is a broadcast, so it's basically saying every machine on this network should see this packet. So as the packet goes through the switch will send the packet out every port, and every host on every port of that switch will see the broadcast frame. And then finally we have multicast, which recall is one to many. So here these top 3 machines are in a destination multi-broadcast host group. So H1 is sending it. Only the top 3 should receive it. And we'll see that as the frame goes through the switch knows, sends out to all of them, and only the ones in the broadcast group, the multicast group will say, hey, that packet is for me. In IP version 4, MAC addresses for multicast start with 01:00:5E. So that's how we know, at least at layer 2, that it's a multicast packet. 727 is a lab. It is really intended and set up to be in the classroom because you need a couple of switches with a couple of PCs on it. We obviously don't have that set up, or we are not meeting in a classroom. We, however, do have a piece of equipment that's very nice called the Net Lab. That is basically physical lab equipment that you can access over the web through a web browser with a web browser front end. So probably what will happen is I'll give you 1 or 2 assignments to log in and kind of get familiar with the Net Lab, and then I'll go back and come up with a way to do 727 on the Net Lab. So when I'm ready to do those, they will appear in Blackboard as well. 731 is talking about switch fundamentals. So down here we have a 4-port switch with 4 PCs connected to it, and we have a shortened version of MAC address just to make it a little easier instead of trying to represent all 48 bits. But before I talk about this, I would like you to recall that I did a supplemental lecture on network devices, and during that lecture I talked about a bridge. The bridge had a bridging table to tell what MAC addresses were on what side of the bridge. And then after I did that, I said the reason we talked about bridges is because I can now turn around and say a switch is a multi-port bridge. And in that case, instead of there being 2 sides of the bridges where we keep MAC addresses, each port is going to have a place to keep track of MAC addresses that appear there. So at this point when we start, this is the MAC address table where we have a port and a MAC address to tell where a device is. When we start out, when we boot or turn on the switch, the MAC address table will be empty. And then what we'll do in this next section is we'll talk about learning and forwarding. So learning is basically learning where devices are and recording that information in the MAC address table. So if I scroll down here a little further, PC A wants to send an Ethernet frame to PC D. So it's going to send the frame. That frame is going to go into port 1. The switch is going to learn that. It's going to make an entry and say, hey, on port 1, I have MAC address 00-0A. So it learns that. Now what's going to happen is it's going to need to forward that port. It knows that the destination MAC is 000D, but nowhere in here does it have recorded what port that is on. So in this case, when it forwards the port, it's going to do something called flooding, which basically means I don't know where the destination MAC is, so I'm going to send this frame out every port other than the port it came in on. So it came in on 1, so I'm going to flood it out ports 2, 3, and 4. Now then, what happens is if PCD is going to send a frame back to PCA, it's going to send it in port 4. Now the switch is going to learn that and say, hey, on port 4 is MAC address 000D. It's then going to, the switch is going to look at its table and say the destination is 000A. I know where that is. That's on port 1. So I don't have to flood this out. It can come in port 4. I'm going to send it out port 1 so that it makes it to the PC with MAC address 000A. And I'm not going to waste time or traffic sending it out port 2 and 3 because there's no need to do that. I know the PC is on port 1. Now then, when A responds back to D this time, same thing kind of happens. It goes in port 1. Port 1 already has a MAC address entry table for that PC. We're sending it to 000D. I know that's on port 4, so I don't have to flood the frame. I just send it out port 4. This is a video that talks about the same thing, but it's only 3 minutes and 4 seconds, so I'm going to go ahead and play it here in the lecture.
In this video, PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame. The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notice it is not a match, so it does not receive the rest of the frame. Now let's have PCB sending a frame back to PCA. The source MAC address of the frame is 000B and the destination MAC address is 000A. PCB sends it to switch S1. S1 notices that the source MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
Okay, like I said, that was an alternate presentation on MAC address tables. If we move down to 735, it is also a video entitled Sending the Frame to the Default Gateway. So before I am going to play this video, but before I do, I want to talk about the default gateway. Basically, when we talk about layer 3, we have networks. And if a host is in the same network, then we know it's on the same LAN, and we know that we can communicate with it directly using its MAC address. If we see that the host is on a different network, then the way we start the packet, the IP packet on its way, is by sending that to the default gateway. So we're talking about layer 3 a little bit. We would transmit the IP source address to the destination IP address, but we would look up and find that that IP is a interface on a router, and it would convert that to a MAC address because we're talking about layer 2 at this point, and it would send it to the default gateway. The default gateway is sometimes referred to as the default router, and on rare occasion, gateway of last resort. But basically, that's the way we need to send a frame or a packet to get it on its destination, which is on another network than the network that the source was on. So this is 2 minutes and 57 seconds. So now that we hopefully know what the default gateway is, we'll play this video.
In this video, PCA is going to send a packet to the internet because the destination IP address is on another network. So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So the Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address, and because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame, which is not in its MAC address table, so it floods it out all ports. PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, and because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
Okay, moving on to 736, we have an activity called Switch It. I think in the last module lecture, or possibly the one before that, we had something called the binary game, and I told you that was one of my favorite activities out of all the Cisco Run curriculum. Here's my other favorite. I think this is a really good graphic, really good activity, and it lets you have several different problems. So basically what you have is it's going to show you the topology over here, including what ports are connected to what. You're going to have a MAC address table. In this case, it's not fully populated because we don't know where 0A is. We do know where 0B and 0C and 0D are. Also notice that we have a hub and we have two machines down here, 0E and 0F. So in this case, not fully populated, but we know where most things are. Then what's going to happen is if we look at the frame, it shows that the frame is leaving 0E, so that's the source MAC, and it is destined for 0F. So basically, you have to tell where will the switch forward the frame. So in this case, it does know that 0F is on the same port, so it will send it, well, it'll know that it's on the same port, so it won't send it anywhere because it knows it will be seen because of the hub. And then it says when the switch forwards the frame, which of the following statements are true. So you can check, you know, it's a unicast, for example. Now it'll be sent out a specific port if it knows where the destination is. If not, it's a unicast frame and it will be flooded out all ports, etc. So you go through and check all the boxes in question 1 and question 2, and then you can check it and see how you did. And then you can ask for a new problem. So in this case, you know, A is sending the frame, the MAC table is almost empty, and it is going from A to C. So I think this is a very, very, very nice activity on switching. And like I said, it's maybe even more my favorite than the binary game by a little bit. So work with this activity until you get a good feel for Ethernet switching. 737 is a lab examining a switch MAC address table. I think this is a pretty important lab. However, we kind of have the same problem as before, which it says the requirements is, I'm sorry, are two PCs and two switches connected together. Since we're not doing this in the classroom, again, I'll have to find some other way to have you do that lab, most likely on the NetLab. So when I get that figured out and ready to go, it will appear in Blackboard. Moving on to 7.4, which is talking about switch speeds and forwarding methods, and also duplex. Basically, there are two methods that we're going to discuss. There's store and forward switching, and then there's cut-through switching. And the reason for cut-through switching is to try to speed up the switching of Ethernet frames. So down here, this is going to demonstrate store and forward, and this is probably how you would assume it worked if you weren't told otherwise, which is we have a frame that the source sends. It goes into the switch. The switch reads the entire frame. It's going to calculate a CRC checksum, which is the frame check sequence. It has one that was in the packet. It has the one it calculated. We're going to see that they match. So since they match, we're going to assume that the frame is valid. And then we're going to send that frame by looking at the switching table to the correct destination. And the device at the destination will read the entire frame and then process it. So that's store and forward. That packet, the entire frame, sorry, I said packet, the entire frame is stored in the switch and evaluated. Now with cut through, there's a couple of different kinds we have, but basically it starts looking at the frame, doesn't bother with the frame check sequence, and will start transmitting that frame out the destination port as soon as it can. So that frame will come in and it will look at the switching table for the destination and start sending that frame. Now, I have seen animations where the frame, like half the frame makes it into the switch, then it shows the evaluation of the destination MAC and the MAC address table. And then while the frame is starting to be sent out here, part of it is still coming into the switch, which is the reality of how this happens. Fast forwarding switching, the second it knows the destination MAC address, it starts transmitting it out the destination port. This reduces the latency and makes the sending of the packet much quicker. There's an alternative to this called fragment free, which it will look at the first 64 bytes of the frame and make sure that that looks valid and we know the source and destination MAC addresses. And then it will go ahead and send that frame out the destination port. Now then, to do this store and forward, to store any part of the packet, we have to have memory on the switch in this case. And that is referred to as buffering. We buffer up or temporarily store information until we know where it's going, and then we transmit that out the destination port, and then we no longer need it. Depending upon the design of the switch, there may be two types of memory. There may be port-based memory, where every single port has memory that is dedicated for it. So it will come in, it will transfer it into a queue for the destination port, and first in, first out, send those frames out the destination port. In the case of shared memory, we have a big memory pool that we record source and destination ports, and they're all kind of intertwined with each other. We need to go back and talk about duplex and speed settings. If you recall, we have full duplex and half duplex. Most modern equipment is full duplex, which means we can transmit in both directions simultaneously. With half duplex, we have to basically figure out what our turn is and attempt to send a frame and hope that we don't have a collision. So when you connect two devices together, the NIC card on the PC and the interface, which is the NIC card for a particular port on the switch, they have to match in duplex and speed. A lot of times you turn on auto negotiation, and what happens is the two devices will talk back to each other, and if they can both do full duplex, they agree to do full duplex. If one of them is a hub, for example, and is only capable of half duplex, it will cause the device on the other end to auto negotiate down to half duplex. Same thing happens for speed. They will negotiate the highest speed that they both support. So this PC will only do 10 and 100 megabits per second, while this switch will do 10, 100, and gig. So they will agree to talk at 100 megabit per second because that's the highest speed that they can both do. So they will negotiate the duplex, and they will negotiate a speed to communicate with each other. Now, if we have a problem and for some reason we've either hard-coded or the auto-negotiated failed, usually it's because we hard-coded, and this switch is set for full duplex and this one is set for half, switch 1 is going to say, hey, we're talking full duplex. I can transmit anytime I want, and you can transmit anytime you want to me, and we can communicate correctly. Well, unfortunately, that's not right because switch 2 is in half duplex, so it's going to see lots of collisions just because S1 is kind of blasting out information whenever it wants and is not doing the carrier sense multi-access collision detection protocol because it's in full duplex. So duplex mismatches are bad. The next thing we talk about is auto MDIX. This kind of goes back to our cables. When we were talking about the cables, we talked about straight through cables and crossover cables. And we said that crossover cables were used to connect like devices, and straight throughs were used to connect dislike devices. The one thing here that we may not have talked about is PC and a router port are considered like devices, so you would need a crossover cable. So technically, to connect these devices shown, we need the type of cable shown. A long time ago, I think Apple was possibly the first people to do this. They came out with Auto MDIX, which is if the cable is wrong, instead of just not working, which is the way it used to be, let's logically switch transmit and receive. So basically, if you connect something with a crossover cable that should be a straight through, it will correct, and vice versa. If you connect a straight through for something that should be a crossover cable, it will correct transmit and receive and allow the devices to communicate with each other. So that's a nice thing. 746 is a check your understanding related to switch speeds and forwarding methods. You can do that on your own. And we'll move to 7.5, which is the module practice and quiz. So 7.5.1, what did I learn in this module? You can go through and read this, but it talks at a high level about the things that we talked about and learned about in this module. And then 7.5.2 is the module quiz for the whole module on Ethernet switching. And as always, you can do that on your own. We had a module group quiz over modules 1, 2, and 3. I believe the next module group quiz is over 4, 5, 6, and 7. If that's correct, we just finished up module 7. And you can watch for that module group exam to appear in Blackboard in the near future.